So there's Bayes' theorem, and there's the prior, and this week is all about choosing the prior, and this video is going to do two things. First of all, it's going to go over the different videos that we're going to see, the remaining videos we're going to see this week, and secondly, it's going to go over the features of the beta distribution. So the next video is going to be on the likelihood function. And you think about what we did last week, we had grid approximation in the globe tossing experiment. Our target was theta, the proportion of the Earth covered by water. Alternatively, we can think of that as the probability that a randomly selected point on the Earth would be water. So we had as our prior, I said we were going to use a beta 5.5 3.0 as our prior. And then our data consisted of y is equal to 4 successes, 4 waters, and n is equal to 10 trials. And so we evaluated our likelihood function, which was the binomial, by keeping n constant at 10, y constant at 4, and putting in all possible values of theta between 0 and 1. We also evaluated the marginal probability of data, and we arrived at our goal, the posterior distribution of theta. But we made a decision. We made a decision about our prior, and in fact, we made two decisions. First, we decided that we're going to have a beta distribution, and secondly, we decided on the parameters. So what I want to think about now is, why did we choose a beta as opposed to something else? A Poisson, a normal, a gamma. And what we're going to see in the third video, in video number 3, is that there's a relationship between the likelihood function and the prior, such that once we know what the likelihood function is, that's going to give us a pretty good indicator of what the prior is going to be. So knowing that we're going to have a likelihood function as a binomial, that's going to drive us towards having the beta as a prior. So that's in week 3. But obviously, if the prior is determined by the likelihood in part, then the obvious question is, where does the likelihood function come from? And the whole point of video 2 is to nail home the idea, where does the likelihood function come from? It reflects the process that gives rise to data. So, in any event, we had a beta prior last week. Why did we choose a beta? Well, the reason we chose a beta is that the beta distribution is the conjugate prior for a binomial likelihood, and that's going to be, this idea of conjugacy is going to be the topic of the third video. So here we have a list of distributions that might serve as likelihood functions. So things like the binomial, the Poisson, the multinomial, the normal, and the uniform. All of these distributions are members of what's known as a particular family of distributions, the exponential family. And although typically when you see the formula for these guys, they look very different, they could all be subsumed under a common formula that looks like this, that, trust me, I do not understand at all. But the whole point is that if we have a likelihood function that is a member of the exponential family, it's going to have a prior, typically, that is also a member of the exponential family that is conjugate to that likelihood. And this conjugacy really just indicates that there's a special pairing, a special relationship, and that's why we often think of these things as being conjugate pairs. In a practical sense, this conjugate pairing is important because it can simplify calculations. So what we're going to see in the first 6 weeks of this seminar, we're dealing with binary dependent variables that are going to have a binomial likelihood function, and the conjugate is going to be a beta. And what's going to happen is that if we have a beta distribution with parameters A and B, and if we have data consisting of y successes in n trials, then we can immediately calculate the posterior as an A star, B star beta distribution, where A star is equal to y plus A, and B star is equal to n minus y plus B. So Conjugacy is very important. The posterior is going to be a blend. The posterior is going to be a blend of the information that's contained in the data and also whatever we specified as our prior. And what video 4 does, it looks at the strength of priors in 3 qualitative categories. The flat, the weakly informative, and the informative. These are the 2 most important. With a flat prior, we're admitting that we have no idea whatsoever what the value of that parameter would be. So essentially, the posterior is determined entirely by the data. At the opposite extreme, we have informative priors, where we do have prior information and we want to leverage that to get an improved estimation of our posterior. The weakly informatives, they're going to play a role in week 7 when we go over hierarchical models, because under certain circumstances, these can be very helpful in improving model fit. The 5th video has 2 parts. One is vocabulary, and there's some of the terminology that we're going to see, and then best practices. So those are the remaining videos that we're going to have this week. And now what I want to do is move on to the beta distribution. And one way to think about that is to compare it with the normal distribution. So there's the formula for the probability density of a normal distribution with random variable y. And here's formula for a beta distribution, probability density of theta. So some differences. In the case of the normal distribution, we have 2 parameters, the mean and the variance. In contrast with the beta distribution, we've got 2 parameters that we label as A and B. And if we think about the mean, it's going to be this thing. If we think about the variance, it's going to be this thing. If we think about the mode, it's going to be that. When we think about the y values for a normal distribution can go anywhere between minus infinity to positive infinity. In contrast with the beta distribution, we're getting upon probability density of theta, but theta can only go between 0 and 1, which makes sense because we're going to have the beta as the prior for the binomial, and the binomial parameter theta can only go from 0 to 1. In terms of shape, the shape of a normal is always bell-shaped. It's symmetrical with the mean, the mode, and the median all being equal. In contrast, the beta distribution can be quite flexible depending on what we choose as our A and B parameters. It's flexible, but not infinitely so. So in the globe tossing experiment, again, we chose this as our prior for theta. And it's probably not a great prior, because what it shows is, if we use 0.5, it shows that we've got a non-zero probability that the proportion of Earth covered by water, it might be less than 0.5, and we know that's not the case. So this might be a better prior to use, because what's saying is, there's essentially no possibility at all in our prior beliefs that the proportion of Earth covered by water is less than 0.5. It has a disadvantage, however, that the modal value here is about 0.86. In retrospect, maybe something like this would have been a better choice. But in any event, those are some of the features of the beta distribution, which is the conjugate prior for the binomial likelihood.